Okay, so now let's do an example where the contour method is not immediate. So find the Laurent series for z, z minus 3, but now the neighborhood is this one. So let me draw it. It's centered at 4. The big circle um, goes from 0 to 8, and the small circle goes from 3 to 5. So this is the neighborhood. Okay. So again, let's look at the coefficient. First, let's do partial fractions to make it a little bit cleaner. So this is a minus 1/3 z and 1/3 z minus 3. Um, so yeah, we take an arbitrary contour c. Okay, so um, right, it will be minus 1/3 z, z minus 2, z minus 4 to the k plus 1, and 1/3 z minus 3, z minus 4 to the k plus 1. Okay. Um, where is it? Now, okay. Um, okay, so here we can apply the Cauchy integral formula for derivatives. So that's fine. And the reason is because the inside the inside C, um, um, there is no pole. So this guy is analytic inside C because the pole 0 is outside because 0, so the pole 0 is outside. Okay, so if we do that, we get 1 over k factorial, and then the kth derivative of minus 1/3 z evaluated at at z equal 4. Okay, so that's fine. This will give us um, minus 1/3 k factorial z to the k plus 1 minus 1 to the k evaluated at z equal 4. So I can just plug it in here. So you get 4 to the k plus 1. Okay, so that's one part. Now, unfortunately, the second guy we cannot apply. So, so let me draw an arrow. So for the second term, um, the Cauchy integral formula does not apply. Okay, and this is because the pole c not equal to 3. So there's a second pole. Let me see what the function is. So right, we have z to the minus 3 and then z minus 4 to the k plus 1. And we have this contour c. So here's 4, here's 3, here's 5. And the contour, this is the contour C, it contains um, the Z not equal to 3 is inside the interior of C. Okay, so remember, in the cos integral formula, this guy should have been analytic, but it's not. So it is not analytic um, inside interior of C. Okay, so what do we do? Well, in this case, all we can do is follow the approach from the book. So for the second term, we use the geometric series approach. Okay, what does that mean? Um, it means that we start with this z minus 3 and we try to write it as z minus 4. Okay, so some expression of z minus 4. Let's see. So um, first we add and subtract 1. So right away we got our z minus 4. Okay, but now we want to expand this, right? In order to write down a Laurent series. So the trick from the book is, okay, when so since we have 1 z minus 4, this implies that 1 over z minus 4 is less than 1, right? If I going from here to here, I just divide. Okay, what does that mean? It means um, that the summation of 1 z minus 4 to the k, starting from 0, you can apply geometric series. Okay, so let me put a minus here. So by the geometric series, you get 1, um, minus minus z minus 4, right? So you get 1 plus 1 z minus 4. Is that okay? So the geometric series is only true when r is strictly less than 1. Okay? So you have to make sure that your annulus gives you the strictly less than 1. Okay, so I have to rewrite this. I factor out the z minus 4, and that gives me 1 over z minus 4 uh, plus 1. Okay, all right. So now I can apply geometric series. And yeah, so I apply geometric series and I get a summation of minus 1 z minus 4, everything to the k. Let me remove the absolute value to see that it's the same. Okay, all right, so that's it. The Laurent series for this guy, it will be minus 1 to the k, and then the power is k plus 1. So altogether, what did we do? We split it, so minus 1/3 right? For the first guy, we can just apply the coefficient, the Taylor expansion. So let me write it from here. So it's this guy. Um, minus 1/3 k factorial minus 1 to the k plus 1, and then, yeah, let me absorb. And then 4 to the k plus 1. And then this guy, all right, let me write down the summations. Starting from z minus 4 to the k. So that's one guy. And the second guy, we have it over there. One second. Let me make sure. Okay, so that's that. And here we have z minus 4 to the k plus 1. Okay, so if you like, um, this is the principal part, and this guy is the analytic part. And this is the entire Laurent series of f, and 1 z minus 4 4. Okay, so that's it. So the reason this is different is because we cannot apply, where is it? Yeah, we cannot apply the what is it? Here. Um, so this is similar to one of the examples in the book. The pole 3 is inside here. So, right, so we have this pole over here, 3, and so we cannot apply the usual cos integral formula. That's the difference. All right, thank you. Okay, so in this case, just go with the geometric series. Do not use the cos integral formula. So, I, in summary, when the pole is on the inside contour, on the inside circle, like in this case, uh, do not apply CIFT. Instead, just use the uh, geometric series approach. Okay, thank you.